All right, hi everybody in HPC. Today we're going to work on a new concept. We've already done all of the integrals, whether they were indefinite without those upper and lower bounds or whether they were definite. We've learned how to do both of those. So the next step up is, well, what do we do if it's not a polynomial string? What do we do if it's not just super simple to just power everything up by adding 1 to the exponent? So today we're going to learn a technique, it's called U-sub, okay? U-substitution. So taking a look at the first one, I can't integrate that the way it is. So one of my options would be to take this fifth power, to multiply and distribute this out 5 times, and then to multiply it by 4x to the third to get it to be a polynomial string. Imagine how much work that would take to do. So we do have a shortcut, but it's got a few steps, and I've written the steps down on the right-hand side for you to kind of follow along. So what we're going to do is we're going to take the more complicated parts and simplify them by just setting them equal to another letter that we're going to call U. So let me erase this, and we'll go through the steps for how to do these. Okay, so my first step is I need to decide, and it won't be perfect every time. There's times you're going to try it and it's not going to work, and you're going to come right back to the step and start over. So I'm going to try to decide what I want to simplify. So I'm going to look for the most complicated part. Now here's the hint. I'm looking for the x that has a higher power than another x already visible. So what I'm noticing right away is that this x to the fourth and this x to the third are good, likely U-substitution options. So if I take the higher one and set it equal to U-substitution, I'm more likely to have this work. Okay, so that's going to be my first step, is I'm going to switch it into U equals. Okay, so I'm going to say, let's say U equals x to the fourth power. All right. So notice that doesn't fix the plus 3, it doesn't fix the fifth power. So I could set U equal to either the x to the fourth or the x to the fourth plus 3 or the x to the fourth plus 3 all raised to the fifth power. My goal is to pick as much as I can. So if I can take more than the x to the fourth along with me, I want to do that, but not so much that its derivative is no longer just going to be 4x to the third, the smaller power. So I think I could still get away with taking this entire grouping symbol and making it set equal to U. So we're going to try that first. Okay, so there is my U substitution. I have now just said that I now want all of this to be equal to U. Okay, so the next thing I'm going to have to do is notice that at the end we also have a dx. Now before we just always told you that had to be at the end. Well, it actually has a purpose. It's telling us to integrate this based on x. Well, now I'm switching it over to u, so I can't integrate a u based on x. So the next thing I'm going to do is I'm going to take the derivative of my u substitution. So it looks like this. The derivative of u is du, derivative of u. Then afterwards, we're going to go back to our derivative rules, and we're going to call this 4x to the third. The plus 3 just becomes a plus 0, right? And then if this was implicit differentiation, we would have added, hey, we took derivative of x on this side. And this is a really important step. And on the left side, we're saying I took the derivative of u, right? 1u would just be 1, and then I'm putting a du to say I took the derivative of u. And on the right-hand side, I took the derivative of an x. So at the end of it, I'm saying dx. I took a derivative based on x. All right, so here's where the fun part starts, is now I get to see if I could rewrite this problem into something I can do. So let's show you what that looks like. So I'm going to first take this entire original amount right here, and I'm going to call that now u to the fifth. Okay, so we're just taking this entire parentheses amount, making that u, but it still has the fifth power, so the fifth power still comes along. I didn't use the fifth power in my u substitution. All right, so right now I have u to the fifth, and I still have a 4x to the third, and I still have a dx. Well, this is just a big mess of letters now. I have u's and x's all mixed together. That's not a good plan. My goal is to switch this entirely over into a u simpler problem. But do you see it? I'm going to switch to a different color. right here is my 4x to the third and my dx, which means I can take these two out and call it du instead, because that's what's on the other side of the equal sign. So it's almost like a magic trick, right? So we're now going to say this is really u to the fifth, and these two parts together are going to just become du. Hey, look at that. I now have an integration that looks super simple. It's just a polynomial raised to a fifth power, and it's telling me go ahead and integrate based on that u. Okay, so that's going to be my next step, is I'm going to try to integrate it based on this. So this would be u to the sixth over 6, and then usually we would add a plus c. But I'm going to substitute it back into x first, and then give it the plus c. There is a plus c right here right now, but it's not my final answer, so I'm just going to wait and remember to put it on at the end. So my next step is to substitute backwards. So now I'm going to take this u and substitute it back. So let me change my color back to the darker one. So now I'm going to turn this into x to the fourth plus 3. Go back up to the top, see how that's equal to u. And I'm going to make that to the sixth power over 6 plus c. And that's my answer. So we temporarily switch the letter into something easier. We take a chunk, the most complicated chunk out. Usually it's the one with the higher power of x in it. And then we simplify that part, and hopefully then it's something that we can actually integrate. This is the only method we have to do integration. Remember, in derivative land, we had power, we had product rule, we had quotient rule, we had chain rule. All of those are not available in integration. The only way to do any of those is to use U-substitution. If you go back and you look at the original, and it was 4x to the third, x to the fourth plus 3, and it was to the fifth power. If I would have said that was your equation, now take the derivative of it, and you're looking at it, so just imagine like the integration was not on there, that didn't have the little swoopy integral symbol. And I asked you, how would you take the derivative of that? And your answer includes either using chain rule or using chain rule, product rule, or quotient rule. You cannot integrate it the way it's written. You're going to have to find a new way to write it. So you'll often hear me say something about, okay, if this was a derivative, are we using product rule? Would we be using quotient rule? Would we be using chain rule? Then we can't do it the way it is and go backwards, right? So now we're just going to practice this idea of switching it to a simpler u problem, integrating it as a u to a power, and then just bringing it back to x and adding the plus c. Okay, so let's go try example number 2. All right, so in example number 2, I look at it and I'm like, oh, I can't do that the way it is. If this was a derivative problem, it would be a product rule with an x and then the parentheses. The fourth power would have been a chain rule, put the 4 in front, keep it, lower it to a 3, multiply by the derivative, blah. Okay, so I'm going to have to try to do u substitution. So I'm going to scan the problem and I'm going to look for x's with powers in them. Right here is an x squared, right here is an x. Okay, I want to pick the one with the higher power, and I want to pick the entire phrase that it's in. Sometimes it's in parentheses, sometimes it's in the denominator of a fraction, sometimes it's under a radical. Okay, so whatever group it's in, I want to take that whole group. That's what I'm going to set u equal to this time. Okay, so I'm doing u equals 3x squared minus 1. All right, my next step, I want to take the derivative of that, and I'm hoping it takes care of the rest of the problem, the x in the beginning and the dx at the end. So 1u, the derivative would just be 1, and then I would say, hey, I took the derivative of u by writing derivative of u. Then on the other side, I would do 6x. So my brain kind of has to keep track of when we're powering up and when we're taking derivative and powering down. Okay, and then this one is going to be a dx. Okay, now let's go check and see what we have, right? We have u right here. That's good. That's going to take care of all that. All right, but I also need to be able to substitute 6x and dx out so that I can replace that last word with a du. I can't just pull out dx and replace it with du. The second equation says they are not the same. You have to make sure you have a 6x dx. Well, I only have an x dx. So on this one, we're going to add in another step. Okay, I need a 6. Well, constants are no big deal. We can bring in constants wherever we want. We just have to balance them. So remember this concept of 6 times 1/6. does not change a problem at all. It's still going to just be 1, right? So if I had all of this times x, I'm still just going to have 1x at the end of it. It's just going to look different. It's going to have numbers in it in the meantime. So I really want there to be a 6 right here. So to balance it, I'm going to have to bring in a 1/6 somewhere. And remember, our rule said that when you're integrating, it doesn't matter whether a constant is in front or inside the integral symbol. So I'm going to keep the 6 inside where I want it to be for du, and I'm going to balance it with a 1/6 on the outside. So this is the step we do when there isn't a number we want. So we're going to bring it in, but we're also going to bring in its reciprocal. And then we're going to use the 6 as part of the substitution, and the 1/6 is going to stay behind, and we're going to have to use it as part of our problem. All right, so now I have 6x, got it, got it, got it, got it, and I have dx, got it. So I should be able to rewrite this as a U integration problem. So as a U integration problem, this 1/6 is just going to come along. I needed it to balance the 6 that I was trying to pull out and substitute out. So then I will have, let's go do the U part first. I'll have U to the 4th, and then I'll have the 6x and the dx turn into du. Okay, and then I look at that and I go, is that something I can integrate? Yes, it's all U's, super easy, just a power. Let's power it up. So we power it up, we get U to the 5th over 5, bring the 1/6 along, and we would normally do a plus C here, but remember, we're going to substitute back. So when I substitute back, we're going to get 1/30th, and then we're going to get whatever is left to the 5th power plus C. So what goes in here? Whatever U was. It was 3x squared minus 1. And that's going to be my final answer. Cool? Now, does it hurt any to write a plus C in the beginning part? No, it really doesn't hurt you any to write a plus C there. The problem is, though, when I integrate it and I switch it back, it might not stay the same C. That constant might have changed in the process. So then I have to keep track of like the first C that I wrote and then the second C that I wrote, and I have to use sub 1 and sub 2, and it's really confusing. So I just wait and I say, I'm just going to collect all the constants at the end and just throw it out there as a big orange plus C. Cool? All right, let's try another one. So on this one, let's do, taking a look, I see a y squared and a y to the 3rd. Are you starting to see the pattern here? So I'm probably going to use the y to the 3rd as my u. And it's in a grouping symbol, right? It's underneath a radical. So let's use the whole thing. Okay, so using the whole thing, I'm going to set u equal to 2 plus y to the 3rd. Then I'm going to do the derivative of both sides. So the derivative of u is just 1, and then you say you took derivative of u, so that's du. On this side, the 2 would turn into a 0 if I took a derivative, so I'd just have 3y squared dy. Okay, let's say I didn't notice that the 3 didn't match and I just started to rewrite stuff. Let's show you what that would look like, right? So I'm going to try now to go and integrate it in terms of u instead. All right, so here I go trying to integrate it in terms of u instead. So I'm going to have square root of u. I'm going to have a dy here. I'm going to have a y squared here, and it's going to look like that. Well, that's a mix of letters. That's not going to work. And then I go and I look and I go, wait, I can take out the y squared, I can take out the dy. I need to create a 3 that isn't there. So I'm going to create it first, balance it with a 1/3. Okay, so this is if the number is not there at all. I'm just going to bring it in and balance it on the outside. So these match exactly with these, and that's just going to turn into the du part of the problem. So I have 1/3. 1/3, the integral of u to the 1/2 power, and now it's a du problem. Okay, let's go find the antiderivative now. Raise the power by 1, so the 1/3 would just follow along. Raise the power by 1 would be 3/2, and then I'd have to divide by 3/2. That looks super ugly. Can I turn it into multiplying by the reciprocal instead? Let's instead call it multiply by 2/3. Cool. All right, so now I have that my answer is going to be 2/9 u to the 3/2. Okay, now I want to go back to x's, right? Or y's. The original problem they gave me was in y's. So if I give them a u answer, they're like, I don't know what that means. I want it in y's. Come back to y's. So we're going to switch it back. Okay, so we're going to call it 2/9 parentheses 2 plus y to the third to the 3/2 power plus c. Okay, and that is totally accurate. Now I might look at the original and go, wait, they had it under a square root. Okay, fair. So if I want to put it underneath some kind of radical, remember the third power stays on the inside. So this is going to be a 2 plus y to the third. So this third becomes the third on the outside. And then the 2 is the index number, so this is just a square root plus c. So either one of these is our correct answer. All right, so you have to check and make sure. Notice when I turned it into dark blue at the very bottom right here, if I looked at it and it had still a mix of letters or I didn't know how to integrate it up, then I probably did not pick the U. Either I didn't pick enough, or I picked too much, or I picked the wrong thing. So us teachers, sometimes we just see it and you don't all the time. So make sure you are asking those questions. How did you know that's what your U that you set was? And there are times where we'll pick the wrong thing and we'll come back and we'll go, wait a minute, can we pick something else? Can we do something else? All right, so let's go through the rest of these here. We've got a couple twists and turns when we get into some trig functions here. We're still not going to be super mean to you, don't worry. Okay, so on this one, let's go do example 4. All right, so in example 4, I'm looking at it and I'm looking for x's. Here's a power of 2, here's a power of 1. Okay, I think I want to take all of this and make it u again. Okay, all right, so I'm going to say I think u is 4x squared plus 2. Take the derivative. I think that's going to be an 8x dx. All right, let's go see if we could rewrite this as a u problem. Okay, so what do I notice? I notice I already have the x, and I already have the, this was a, that's a mistake. This should be a dx problem. I apologize. And I already have the dx. I need that 8. I need to get that 8 in there. So I'm just going to go back to the original, throw it in here, throw in a 1/8 here, and just move forward and go, okay, now I have the 8. Okay, so integrating it, this 1/8 has to come along, but I'm going to start out with, under here, square root of u, and then the 8, the x, and the dx become du. So I just need a placeholder number on the top. That's doable. I can do that. I have to rewrite it first, but I can definitely do it. So this is u to the negative 1/2 du. Raise it up by a power, so we're going to add 2 over 2 to this. So if I add 2 over 2 to this, I'm going to get u to the 1/2 power over 1/2 with a 1/8 in front. So again, I'm going to choose to multiply by the reciprocal. So this is going to equal 1/4, 2 over 8 is 1/4, and it's going to be u to the 1/2. Okay, so now I want to go back. I want to go back to the original problem that was originally in x's. Okay, so that's our next step, is we're going to bring it back to the original letter. So same substitution, I have a 1/4, now I have this as a 1/2, I'm going to throw in the plus c in here, and I'm going to go find what u was set equal to in pink. That was 4x squared plus 2, and if I want it to look like the radical like it was originally, right, the 1 would have been inside as a power, I don't need that, 4x squared plus 2, and the 2 in the bottom would become the index number. I don't need to write a 2 when it's a square root. So either one of these answers would be correct. Okay, this is it. This is the only way we have to integrate something that would have looked like in a derivative problem, product rule, quotient rule, or chain rule. All right. All right, now let's go into some of the trickier ones. So here's a trig function one. All right, notice there's only one x. Okay, but that's okay. My problem is when I integrate cosine, I only know how to do cosine of x. I don't know how to do cosine of stuff. So again, if I were to take this off and said, hey, this is a derivative problem, and I were to say y equals cosine of 5x plus 2, and you'd be like, oh, hey, no problem, that's going to be sine of 5x plus 2. Oh, wait a minute, it has chain rule, right? Chain rule is this times 5 in front. That's the thing that tells us I cannot do this the way it is. Okay, so I'm going to have to go backwards. I'm going to have to do a U substitution for this one instead. So I'm just going to pick the thing that is making this difficult. If it was just cosine of x, I could do it. Okay, so then that's what our U substitution is going to be. 5x plus 2. Take the derivative of the left, take the derivative of the right. Do we have everything we need in order to convert it? Well, let's go look. So I know this is going to turn into cosine, and I know it's going to have a u right here. But in order to get rid of this, I need a 5 with it. I don't have a 5, so I have to create a 5. So 5 on the inside so that I have 5 dx. Balance it with a times 1/5 on the outside, and that's just going to come along in our answer. And now I can switch it to a du problem instead. So I substituted out the 5 and the dx as du. All right, so that I can integrate. That's not so bad. That's just going to be sine of u. Yeah, that works. Okay, so now we just have to go backwards. We need to bring it back into x's. So bringing it back into x's, we're going to have 1/5 sine of u was equal to 5x plus 2, and then add in the plus c. Ooh. All right, ready for a really super challenging one? I think this is our last one. Okay, another trig function, but now look at that. The 3x, if we're doing derivative, would definitely have been chain rule. And then we've got the first one that's really sine of 3x to the 4th power, right? So let's switch to a different color scheme here. We'll do a red one again, okay? All right, so what am I going to set u equal to, right? So another way to write this would be sine of 3x grouped together, 4th power, cosine of 3x dx. Okay, they were just avoiding all those parentheses by putting the 4 after the word sine. That's what it really looks like. All right, so just switching 3x to a u, we could try that if we just set u equal to 3x and du is equal to 3 dx, then what would we get? We would get sine of u to the 4th power, cosine of u to the 1st power, and then we would need a 3 here and a 1/3 here, and then this could be du. You know how to integrate that? Isn't that like product rule if it was a derivative problem? So I can't do this yet. I haven't substituted enough. I'm not there yet. Okay, can you see how it's sine of u times cosine of u with the 4th power? Sine of u and cosine of u, if this would have been a derivative problem, you would have had to have used product rule. So I can't do integration backwards when it looks like this. I only can do basic, simple polynomial strings with one thing to a power. So I probably didn't pick enough. I probably need more. So I'm going to go back, I'm going to backtrack here. We're erase, 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 erase. And I'm going to see what else I could take other than 3x. So now my choice is, if I'm going to increase 3x, I could either make it sine of 3x, or I can make it cosine of 3x. Under the rule of pick the more complicated, would it make sense that I'm going to pick sine of 3x because it already has the added grossness of having the 4th power on it? So I'm going to pick that one. So du then would just be cosine of 3x. Oh, wait a minute. It's okay to have chain rule in here because it's a derivative problem. So times 3 dx. Okay, so how is that looking now? Let's go try. Let's go see if we're able to switch this one over. So this would have turned into u to the 4th for this part, right? Since sine of 3x is u, this would just be u to the 4th. Cosine, ooh, that's in there too, and the dx is. But I also have to deal with the 3. So I'm going to throw a 3 here, a 1/3 in front, and I should be okay. That worked. So this is what it looks like to guess and check and then go backwards. All right, so let's go and do the integration of this. U to the 5th over 5, we'll have the 1/3 carry along. That's going to be 1/15 of u to the 5th power. Let's go back to x's. So repeating using the same u substitution, we're going to call this 1/15 of sine of 3x to the 5th power plus c. And that's it. All right, we'll practice this lots, you guys. We'll see you later.